Okay, so we're going to cover now improving what we can control. Some things we can't control. The size of the copper on our system, the size of the copper used in the coils, the 1/4 inch access fittings. Those things that we can't control, we're not going to worry about. The things that we are going to worry about are the things that we can control. And to better illustrate that, I wrote them down on the whiteboard. So improve what we can control. The vacuum pump, choose the right pump. The vacuum manifold, build the right manifold. Conductance ratio, directly related to our vacuum manifold. Flow, directly related to conductance ratio. Again, what we can't control, copper size, access, all those things that we can't. So what we're going to improve on are it's really two things, the pump and the vacuum manifold, because the conductance ratio and flow, the higher we have the conductance ratio, the higher the flow we have, and that's how we're going to build our manifold, so we can control the pump and the vacuum manifold. And we're going to pick the right pump, and we're going to build the right manifold, or buy the stuff to build the right manifold. Very simple, very easy, and that's what we're going to do right now. We're going to build a manifold. Alright, pump sizing. Everybody always talks about pump sizing. I've heard the CFM squared and I've heard CFM cubed. So just taking a look here, if you have a 3 CFM pump, squared, that's 9 tons. Cubed, that's 27 tons. 8 CFM pump, squared, 64 tons. Cubed, 512 tons. The review of engineers, the review of vacuum for service engineers says a 3 CFM pump is good to about 10 tons, and a 6 is good to, I don't remember what it said, 50 tons or something like that. Didn't give a formula, it just stated it. And it said based on practical experience, whatever that is. The CFM isn't the only consideration. It's just not the only consideration. Other things to consider are how much oil does it hold? How easy is it to change? Can you get the oil reservoir clean? How many ports does it have? 1? Is it 3/8? Is it 1/2 inch? Are you going to have to change it? Are you going to have to add to it? The cost. How much does it cost initially and in the long run? If you buy a $300 pump, but you have to buy one every 2 years, then you're probably not doing yourself any good. Weight. I don't want to carry a 35-pound pump around if I can have one that weighs 28 pounds or even 24 pounds. And what about repair? Field repairable? Is it easily field repairable? Do I have to send it in? Talk to other people, figure out the problems they've had with pumps and whether or not warranties were honored or rejected, or when they did buy the parts to rebuild it, would it have been cheaper if include their labor to just buy a new pump? All these things have to be considered. But for strictly sizing considerations, I tend to agree with the CFM squared model, where 3 CFM is for 9 tons and 8 is up to 64 tons for a regular pump with just 1 port on it. But again, I've used my 3 CFM pump on 15 and 20 ton machines and had no problems. It works beautifully. I say all this to say, because we're going to be reviewing the TES 8 from Appion, and they pull 1,500 ton chillers and 250 ton chillers and all these big giant rack systems with this TES 8, and not only do they do it, but they outperform 20 CFM pumps while doing it. So it takes 20 hours instead of 4 days versus a 20 CFM pump. And it's less about the pump, the size of the pump, and more about the manifold and the conductance ratio and the flows they get out of it. So, what size pump? You control that. If all you ever do is residential and you're never going to do anything over 5 tons or even 10 tons or 15 tons, a 3 CFM pump makes perfect sense. By the same token, if you do light commercial and you're going to be getting into some 25 ton stuff, or even 50 or 75 ton chillers and things like that, then you may want to look at going with a 6 or 8 CFM pump. Again, multiple connections, a better vacuum manifold. Those are the key things, the real key things. The main thing to consider when you're buying a pump, especially for long term, is the oil. Can you clean the reservoir? Can you see the reservoir? Does the oil that you do see give you a clear indication of the true state of the oil? How many ports does it have? How much does it cost initially? How much does it cost in the long run? How much does it weigh? Is it 24 pounds or 38 pounds? And the repair. Can you buy the parts and repair them with normal tools? Or do you have to send it in and have it repaired? Or is there 6 weeks lead time on the parts? All those things need to be taken into consideration. So we can control the pump, the size, the long-term cost, and the short-term benefits of the features that are built into it. All right, part 2 of the equation on what we can control. Number 1 was pumps. Number 2, vacuum manifold. We're going to build the manifold. You're going to buy a manifold, you're going to buy fittings, you're going to buy hoses, whatever. From the unit to your pump is the vacuum manifold. That's what we're talking about. So 2 things really play an important factor in the manifold. And we're going to cover both of those right now. Conductance ratio and conductance speed. Conductance ratio is nothing more than a ratio, and the mathematical formula to find that out is the inside diameter of the line raised to the 4th power. So come right down here and look. 1/4 inch has a ratio of 0.004, 4 thousandths. 3/8 has a conductance ratio of 0.020, 20 thousandths. 1/2 inch has a conductance ratio of 0.063, 63 thousandths. So you can see the ratios increase with the size of the pipe. But what does it really mean? Here, 1/2 inch versus 1/4 inch is a 15.75 increase. So 1/2 inch has almost 16 times the conductance ratio of 1/4 inch. 3/8 versus 1/4 inch, 5 times. So 3/8 has almost 5 times the conductance ratio of 1/4 inch. And the reason we need to know what the conductance ratio is to find the conductance speed, which is our flow in CFM. Conductance speed is 520 times d to the 4th power, which is our conductance ratio, times pressure in millimeters divided by length in feet. So pressure in millimeters, length in feet. And I'm going to erase this and I'm going to draw some more numbers on the board, and I'm going to show you what it means in the real world as far as flow. But conductance ratio, inside diameter to the 4th power. So here at 1/4 inch, it's 0.250 times 0.250 times 0.250 times 0.250. That's what it is. You get that number. Same thing with 3/8, 0.375, 1/2 inch, 0.500. Do the math. You do it. You'll come up with the same thing. It's this. 1/2 inch has 15.75 times the conductance ratio of 1/4 inch. We're going to convert it into flow next. Alright, so how do we convert all this into flow? How do we know what we're flowing? Well, it's not that hard. We use the formula 520 times the inside diameter raised to the 4th power times the pressure in millimeters divided by the length in feet. So for this little chart that I drew here, we're using 500 microns, which is 0.5000 millimeters. So 5 thousandths of a millimeter, 0.500. Here we have 1/4 inch, 3/8, and 1/2 inch. Down here we have lengths, 3 foot, 5 foot, 6 foot. So we have both variables in here. So for 1/4 inch, here's the inside diameter raised to the 4th power, our conductance ratio. Here's the conductance ratio for 3/8, and here's the conductance ratio for 1/2 inch. So for 1/4 inch, at 3 feet. Conductance, the CFM is 0.347. 0.347. 3/8, 1.733, about 1 1/4 CFM. Half inch, 5.46, almost 5.5 CFM. Keep going down the chart. The longer we get, the worse it gets. 0.208 for quarter, 1.04 for 3/8, 3.27 for half. For 6-foot hoses, 0.173 for quarter, 0.866 for 3/8, 2.73 for half. So you can see very easily, the differences. I mean, the longer we go, the fewer CFM we have, the longer the hose is, and the smaller the hose is, the fewer CFM. So at 6 feet for half inch, we can only move 2.73 CFM through that hose, and for quarter inch, we can only move 0.173 CFM through that hose. That's in a perfect world. That's no turns, bends, crazy fitting, none of that. So what does that translate into? Down here in this little column, this is half inch versus quarter inch. So half inch hoses that are 3 foot long versus quarter inch hoses that are 3 foot long equals 15.73 times greater flow. By using half inch hoses, you increase the flow by 16 times, apples to apples. And that holds true for every formula on down the line. It changes just a little bit, 15.72, 15.73, and it just goes on down. But basically it's 16 times the flow. However, I know most guys are using 5-foot hoses, refrigerant hoses. So what I did is I took a half inch hose that's only 3 foot long versus a 5-foot hose that's a quarter inch diameter, and look at the gain, 26.25 times. So by going to a half inch hose that's 3 foot long instead of your quarter inch hose that's 5 foot long, you're increasing your flow by 26.25 times. 26.25 times. That's phenomenal. Dave Boyd says a half plus a half plus a half equals 10 times. Well, a half plus a half plus a half may equal 10, but if you cut the hoses in half, it equals 26. So the point is, bigger diameter, smaller length equals more flow. We see it all the time. We do cap tube, we have to do cap tube sizing, we have to do distributor tube sizing. It's no different than looking on a cap tube chart for bore and length. The longer it is and the smaller the diameter, the more pressure drop. No difference here. It's the exact same principle, because really when you think about it, a cap tube doesn't work under pressure, it works under vacuum. As fast as that compressor can evacuate the evaporator is how fast it's going to come through. It all has to do with pressure drop. So the next question I know is going to be, but we only have quarter inch fittings, and if we only have quarter inch fittings, then what does it matter if we can move 5.5 CFM through it? That's a good point. So quarter inch fitting with the Schrader core removed, you're going to move about 2.8 CFM through that fitting. Now if you can hook up to 2 fittings, then that becomes what? 5.6? Okay, 5.6, we'll go with that. So really, you can move 5.6 CFM. We'll go up our chart here, and so 2.8, we could have a half inch hose that's 6 foot long, get very close to 2.8, or if we back it up to 5 foot long, we can do 3.27, got plenty left over. The thing that this doesn't take into account is bends, turns, 45s on the ends of the hoses. It doesn't take any of that into consideration. So you have to take all that into consideration. It's just far too many variables. The only way to do it realistically is set up a lab with the exact conditions and actually do a hot wire anemometer across it to see what you're moving. So what I tell you is, for the same amount of money, virtually, just buy short, big hoses, right? Oversize it by double. If I have one hose that's capable of moving 5.46 CFM, then I know, or I have a reasonable suspicion or a reasonable, I have reasonable assurance that by oversizing the hose to 5.4 CFM, almost double what my 1/4 inch fitting can move, that I'm going to be able to overcome those 45-degree fittings and bends in my hose and things like that. So, yes, in a perfect world, all else being equal, you would only need to have a hose that moved 2.8 CFM. But in the world we live in, it's just too much math. Nobody's going to do it. 1/2 inch hoses, 3 foot long. 1/2 inch hoses, 5 foot long. I wouldn't go over 5 foot. Unless you just had a big system and you needed that extra long reach and you could hook up 4 of them or 6 of them, then I'd go over 6 foot long. But not. If it's going to be over 6 foot long, I'm moving up to copper. I'm moving up to 7/8 or 1 inch or something like that, even steel pipe. But we're not going to do that because 6 foot hoses on a system, hook 4 of them up, hook 8 of them up, hook 4 1/2 inches and 2 3/8 or whatever, and overcome all that nonsense. Then you don't have to do all the extra plumbing. So 1/4 inch fittings, 2.8 CFM. My 1/2 inch hoses will do 5.46 CFM. The next diagram I'm going to show you is the choke point and why we need 5.46 CFM, why we need to be able to handle that 5.46 CFM and what it means. So I'm going to pause, redraw, and be back. Alright, look at the diagram. Look at the diagram, look at the diagram. It's what I call a choke point. This is our pump, our 8 CFM or 6 CFM or whatever size pump it is. And again, 500 microns, 0.500 millimeter. So here's my access fitting and here's an access fitting. It's my 1/4 inch Schrader valve, 2.8 CFM, 2.8 CFM. So, in a perfect world, theoretical flow, I have 2.8 CFM and 2.8 CFM. As soon as it goes into my T, or my vacuum manifold, or my mega flow, or my whatever you call it, if I have a 1/2 inch bore, now I have to deal with 5.6 CFM. Okay? So we're taking these 2 CFM and we're turning them into 5.6 CFM. So this little 1/2 inch down here, which is about 6 inches, 8 inches long, needs to be able to handle 5.6 CFM. A 3-footer handles 5.46 if it's 1/2 inch, so I know my little 6 incher is going to be able to handle that. 2.8 CFM, 2.8 CFM. This is based on 1/2 inch hoses that are 3 foot long. Each one of these hoses will handle 5.46, so I know whatever variables are causing even further loss of flow other than just the pressure drop in my hoses, I'll be able to handle it. But let's just look at it. If I had 6 foot hoses here and here that were 1/2 inch, it'd be 2.73 CFM and 2.73 CFM. I know 2.8 and 2.73, not a whole lot of difference, and maybe you're right. Maybe it doesn't make that big of a difference. But this is theoretical flow. Bends, 90s, turns, all that stuff has an effect, has a net effect of pressure drop on this thing. So if you're already starting out low and then you throw those variables in there, which we don't know what they are, you could be somewhere around, let's just say it's half. Let's say it drops down to 1.3 CFM or 1.2 CFM. Again, same thing with 3/8. If we switch over to 3/8 hoses here and here, we're already at 1.73. And then throw in the other variables that affect pressure drop, 90s, turns, blah blah blah. Then now what's going on? 1/4 inch, 0.346. You're only going to move. You're moving less than, well, you're moving 1/3 of a CFM, not 1 CFM, 1/3 of 1 CFM. So forget 1/4 inch, forget 3/8. You're not even moving theoretical flow. 1/2 inch, 6 foot hoses, 2.73, 3 foot hoses, 5.46. Yeah, but how can that be? We're used to thinking of pressure and and you know, you can't squeeze more and get more out the back and all that, but it's not about stop thinking about pressure and start thinking about flow. As we, you know, start bringing these down in here, we want to keep that velocity up, right? We don't want to restrict it. We don't want to have good velocity here, and then by the time it gets here, have no velocity, because we've lost it all due to friction loss. Too much. We want the velocity to be maintained, which is why we go with a very, very short 6-inch hose from our manifold to our pump. We keep it as big as possible, 1/2 inch, man, even 3/4 inch. That would be cool. Big old 3/4 inch hose on there. Really suck it down. And then, of course, thinking about manifolds here, you know, the Mega Flow manifold is a full 1/2 inch. 1/2 inch bore everywhere. Every hole they punch in that thing is a 1/2 inch bore, with the exception of the two for the gauges. Everything else is a 1/2 inch hole. My manifold I use is a 1/2 inch bore. You know, your refrigerant gauges, you know, with full bore 3/8 inch, whatever, man, throw that crap away. You want a 3/8 bore? Why? Why do you want a 3/8 bore that's only going to move 1.73 at the maximum? That doesn't count having to go around valve stems and all that crap. Forget about it. Forget 3/8 bore. Don't let them sell you that crap, and don't buy it because they say it's better. It's not better. 3/8 bore is nothing. It's limiting. That's what it is. A 3/8 bore on a refrigerant manifold, if you're using it for vacuum, is costing you money. Don't let them BS you. So again, 2.8 CFM is the max we're going to get out of it. 500 microns. 1/2 inch hoses, you can see here, translate into maximum CFM. Yes, 5.46 CFM is a whole lot more than we need, but because we don't know the other variables, and I don't know how to calculate them and show that, we're going to go as big as we can on CFMs to overcome those. Again, we're moving theoretically 5.6 CFM at our pump here. So, I mean, if we're looking at this, then, you know, maybe a 6 CFM pump might not be a bad idea. Like I said, though, in the real world, a 3 CFM pump works. I mean, the pump down time between 3 CFM and 6 CFM on a recovery drum is seconds. I mean, it's seconds. You know, it's, don't hold me to this, but it's like 6 minutes and 35 seconds versus 6 minutes and 47 seconds. It's ridiculous. A 6 CFM and a 3 CFM. All those being the same, except the pump and the CFM. It was even the same pump manufacturer. It was a JB3 and a JB6. But we're going to do pump downs later on with the Appions, so you'll get to see those numbers. But anyway, you know, total CFM theoretical, CFM from each line. Now, if you have multiple ports, like say it's a heat pump, and you could hook it up to a true suction port, or you took the time to solder in extra ports, maybe at the evaporator, hook another vacuum pump up there, then you know, you're going to even do better. You're just going to do a whole lot better. The more hoses you have coming into here, the better it is, which is one of the things I like about the TES 8. It's got 4 ports on it. I mean, I only ever used 3. I mean, I never used a 1/4 inch, but those 2 big 3/8 ports and that 1 big 1/2 inch port, and I can put a tree on there and bring 6 hoses, 7 hoses into that thing. It's phenomenal. Good stuff. Good stuff. So you can see how the conductance ratio, translates directly into CFM. I mean, that's what we're doing here, right? We're finding out the CFM through this thing. You know, the things we can't change, copper tubing sizes and all that stuff, forget about that. Forget about it. Look at the math. Look at the math. I know it's only theoretical, but look at the math. If you want to pull 6 CFM, it's entirely possible. Well, 5 2/3 CFM is entirely possible with 2.8 coming out of 1. And it really is entirely possible if you hook up 2 1/2 inch hoses and then 2 3/8 hoses. to the system. It's entirely possible to get 6 CFM out of that system. And again, we're talking about 500 microns. We're going to talk about flows under a vacuum here in just a second. I'm going to erase, I'm going to rewrite, and I'll be right back. Right, flow. We've been talking about flow, CFM, and everything else. And I know invariably, because it always comes up, but Brad, how can you be talking about CFM when all we're doing is moving molecules? Well, that is all we're doing, is moving molecules. And CFM is just a whole bunch of molecules at once. So in the book, they tell us about 3 forms or 3 states of flow in a vacuum: laminar, transitional, and molecular. And they tell us how to determine what state that we are in. It's pretty simple, actually. See where we are here? Perfect. So 3 states of flow: laminar flow, also called viscous flow; transitional flow; and molecular flow, also called diffusion. Diffusion? No. I think it's diffusion. Anyway, and it's just a mathematical formula. So laminar flow is when it's equal to or greater than 100 divided by D, where D is the interior dimension in inches of the line. Molecular is when it's equal to or less than 4 divided by D, the ID of the line in inches. So this is in microns. So 100 divided by D, if it's equal to or greater than that, we're in laminar flow. If it's equal to or less than 4 divided by D in microns, we're in molecular flow. Between the two is transitional flow. It's really that simple. So here we have, bam, half-inch hose. Half-inch. Do the math. Equal to or greater than 200 CFM, laminar flow. Equal to or less than 8 CFM, molecular flow. So between 200 CFM and 8 CFM, we're in transitional flow. What that means is, at 200 CFM, we have to be below 200 microns to even start to get into transitional flow. What that tells us is we very rarely get out of the laminar flow region because, well, most of us, not most of us, but those of us who use half-inch hoses, because we don't get into transitional flow until we're below 200 microns. So, you do the greatest amount of work in the laminar flow region. You're moving more in that region. So the goal is to stay in the laminar flow region for as long as possible. So you look at 1/4 inch down here, and laminar flow ends at 400 microns, and molecular begins at 16, and transitional is in between. So it's pretty simple. Could these conditions exist inside the system somewhere? Yes, they could. Could they exist at the Schrader valves? I guess they could, unless you were actually taking a micron reading right there at it and knew for sure exactly how much it is. So, sometimes when we see our vacuums start to stall out at about 250 microns or 275 microns, if you're going down below that, for whatever reason, then there's likely you have entered the transitional phase, and what that is all those unknowns variables I was talking about earlier have added up somewhere, so that the total diameter of the entire system is between this and this, and you're in that transitional flow. But by and large, we don't deal with that. We get to 500 microns or 400 microns, we're done. And again, the longer you stay in laminar flow, the faster you're going to get done. That's just how it works. That's the way it is. So laminar, transitional, molecular, 3 states of flow. We're talking about CFM, we're talking about laminar and transitional. By and large, by the time you get to molecular, you're not talking about CFM anymore. You are, but it's teeny, teeny, tiny. And that's an area that we don't even play in. I don't even know who has a pump rated for 8 microns or even 16 microns for that much. I had one pump that got down to like 18 microns one time, blanked off with the vacuum gauge right on it. That's the only one I've ever had, and that was 8-10 years ago. And it was a fluke, I think. So anyway, so that's it for episode 5. I'm going to go in, render this, get her done, and be back out mañana with the TES 8, the Mega Flow kit, some oil, some pump down tests, and you know, the exciting stuff. So I hope you learned something. That's probably going to be it for the whiteboard. There might be a little bit more, but not a whole lot. And if you have any questions, or you're sitting at home taking notes and doing math, and you find me wrong up here, which you could, it's very easy. I'm not a math magician. I'm just a HVAC tech. Email me, send me a link, whatever you do, let me know so I can correct it. All right, see you in the morning.